So what I'd like to do is show a framework in terms of addressing many of the questions relating to climate change and forests. And so what this framework is really to address the front end, which relates to the climate. We have a tendency to rely on other people's inputs. I think we need to have capacity in New Brunswick to deal with these questions of climate on almost on a real-time basis, which at this point we don't have that capability. Just last year, a PhD student came to me, and his area was actually in this area. He has a PhD from Italy. He's originally from Cairo, and most of the simulations relating to the climate aspect of this presentation is work done by him. It's interesting because he's able to look at climate, but also daily weather events, which is really a fine detail that sometimes we need to take into account as well. So here's the framework. The first part of the framework is this regional climate model. That's the capability I thought New Brunswick needed. We depend a lot on using ORNOs or even other data sets, but we don't have control over those data sets, so we just use them. I think we need to have a capacity to actually moderate or change those data sets according to our own needs. And then the second part, or the back end of the presentation, relates to the landscape forest model that I'll present to you. It's still in a work in progress. It's not completed, but I'll just show you some results from that work. The middle part is, the middle part we're not going to talk about. That middle part relates to how to make the connection between climate models and the forest models. And the resolutions that you're dealing with climate models, they come in typically at the global climate models. They have a scale, a very huge scale, that only one point actually lies in New Brunswick. When I'm talking about points, I'm talking about the grid system that they use. One of the junctions or nodes falls in New Brunswick, which is clearly not sufficient enough. And so we need to have methods to allow us to go from these regional climate model. We use the global climate model to drive the regional climate model at a finer resolution, but even then we still have to do some downscaling. And the type of downscaling we use is a procedure that I developed over the last few years, based a lot on ETF funding that I received over the last 5 to 6 years. So let's start first with the regional climate model. Unlike the global climate model deals with a very coarse resolution. The regional climate model, as indicated, uses the input from the global climate model as drivers for the regional climate model. The nice thing about the regional climate model, typically we like to downscale. This type of downscaling is based on dynamic system opposed to using simple statistical relationships. I'll talk a bit more about that dynamic aspect of regional climate models. Here's the global, the GCM. Those are the global circulation, very coarse resolution. And typically we'd like to get information at a much finer resolution for an area of interest. In our case, might be all of New Brunswick or parts of New Brunswick. So regional climate model has an advantage in terms of mechanistic downscaling, okay, dynamic downscaling. It provides high resolution simulation and enhanced accuracy. It allows us to make relationships about the change in the land and how the land interacts with the atmosphere. Those are things that, that normally we don't address in terms of downscaling. It addresses orographic force in climate. That means how the topography, the land use, the movement of water over the landscape, how that impacts the local climate. So that addresses things like temperature differences, convection, clouds, precipitation. All of these are addressed in these regional climate models. And typically, this particular model that I'll refer to is actually designed or optimized to run on PCs. It takes a lot of time, but still can be done. And the last point relates to the low computational costs associated with this downscaling. Here's a shot, a simulation for Hurricane Arthur. You'll see about July 5th, you'll see this swoosh of blue colors. There he goes. That's Arthur. Now we have that capability. If we're looking at forestry from a wind disturbance perspective, we can actually get these values from this type of modeling. Here is during the same time, relating to the passing of Hurricane Arthur. These are precipitation fields, and you see that band, that's actually the hurricane going by. So you have the capability to determine both in terms of timing, but also the intensity involved in terms of the delivery of precipitation. Other products that are produced by this regional climate model are other things like runoff. This is at 5 kilometer resolution. This is for a runoff, different times, just to show the importance of this type of information. So you get much more information than simply doing a statistical downscaling. So other variables that are available to address plant growth would be temperature, growing degree days, cloudiness, surface incidence, solar radiation, very important one, which typically we don't address. Precipitation, water vapor pressure, a lot of meteorological variables that technically we don't address at all in terms of looking at how climate impacts forests. Here is another feature of the model. This plume that you see here, that's the plume that was generated by the, or at least the, remember the Minto tire fire? Because there's a huge environmental impact associated with the turning of the tires into a liquid, gases, and all that. So there's an interest in following through and trying to look at the impact of that particular fire. And so what we have here is that this is the plume associated with that fire. Note that the timing here is different. We don't have the December 2019 data, but the point is we can do it given the appropriate forcing information from the GCM. So this is just an aside to show its flexibility and the type of information you can actually generate. An important aspect to this model is validation. How well does it actually represent temperatures or precipitation, any other variable over a region of eastern Canada? In terms of each of these points, these represent individual weather stations. Their colors indicate the level of correlation between the actual data and the model data. So in terms of the red points, you're looking at correlation coefficients of over 90%, indicating a very good relationship. In other points where you get into the blues, the correlation drops. And so those are things that we have to look at to try to make the model even better and more representative of all of New Brunswick, opposed just to some parts of New Brunswick. Okay, that was the front end. The back end now relates to looking at forest landscape model, and the approach that's being used here is to look at it from a landscape perspective. For doing that, we can also look at points on that landscape as representative of various forest types. The actual model itself is composed of two parts, or two modules. The first relates to the biophysical variables. So that part that I have the X in terms of the downscaling part at the resolution that's required, here the resolution is at 20 meters. So from GCM down to RCM, we're going from 45 or 100 and some kilometers to 45 kilometers, potentially down to 5, and potentially down to 20 meters. In terms of the biophysical variables relevant to tree growth, the first one relates to illumination angle. Where's the sun at any given time of the day and year? The position of the sun has a significant impact in terms of growth, given that it's related to how much shading there is in the understory. The sunlight, of course, important in terms of photosynthesis. Air temperature in terms of growing degree days here is also an important variable to define where certain forests or if certain trees will grow or not grow. Soil water content and wind speed. So this gives you the biophysical variables that relate to plant growth, and this relates to the actual forest dynamics. So the information that's generated here in terms of these maps is used to drive the forest dynamics part. The forest dynamics part is applied at the cell level, at plot level, cell level, and potentially across entire landscapes. And the currency of the model is biomass. You can use others if you're interested, volume, whatnot. In this particular case, I use biomass. So here are some examples of some of these annual maps, and they're represented here for all of New Brunswick. As you can see, there's variation as you go from south to north of the province and from east to west. And then you see the same type of pattern, or slightly different patterns, but still quite consistent what we see with relation to solar radiation. Here's for precipitation, and here's for average wind speeds. And the maps are available for every year from 1985 to 2100. So as you go beyond 2018, it becomes part of the results from the RCM, Regional Climate Model. So if we want to look at the details, the software that's used for developing this is very object-oriented software. And this software is applied for individual cells in a digital elevation model, so at high computational cost, but it can be done. And each part represents an aspect of forest growth. The first part this part here deals with tree growth. So this is the accumulation of tree growth over time in terms of both DBH, but also in terms of height. They're related, and it's done through an expression that looks at the change in DBH over time. The upper part deals with elements of forest, relates to death and birth processes. Here the death processes would be due to senescence or simply the plant through a stochastic process, it gets eliminated. And while the birth processes will deal with regeneration. So you start with little trees based on the overstory will define the forest over time. This part here relates to the intertree shading. So one of the elements of competition relates to the competition in terms of sunlight. So some plants are tolerant to shade, while others are not so tolerant. And so you put that in the mix, and that will determine what comes out in the long run. And based on where you happen to be in the landscape. So the landscape, the topography has big influence on how things evolve over time for a given piece of land in a particular part of the landscape. So in terms of the biophysical variables, there is a model out there that can be used to upgrade these maps, these biophysical maps, that takes into account the sunlight and the precipitation and does a balance between the two. It's not a simple energy balance, but actually it's a water balance plus an energy balance to give us an understanding how much water is actually in an area and how much water would be evaporated. This is done at individual cells, and each cell you can envision that there's force. And a certain amount of that precipitation falls in a given cell. A part of that precipitation is lost due to interception. Whatever gets to the surface, then you do a water balance in the soil to determine how much water actually stays based on the fact that the cell might be on sloped land. So that water will tend to flow downhill. So, but the interesting point about that is that you can calculate for every cell that makes up this digital elevation model, you can calculate how much water would remain in that soil. Here's a close-up of available global solar radiation. Here we see that there is variation, where it's slightly darker, indicating a north face slope, and here where it's lighter yellow, south-facing slope. So there will be differences in terms of the amount of sunlight available. As indicated before, the illumination angle, an important aspect, especially in terms of addressing that intershade competition, and also in terms of driving regeneration. Now, in terms of looking at the climate, this is an average. These two lines represent an average for all of New Brunswick. The two lines indicate what the projections are based on RCM models that happen to be outside the province from Quebec, Montreal. And the red line represents the projection that is expected for the average of New Brunswick. So it's not just one point. So you can view the projection, all the weather stations that make up New Brunswick. This is an average representation. So the red line here indicates an increase over time, where this is historical, and both, of course, the historical for both the two climate scenarios, RCP 8.5 and RCP 4.5. Of course, historically, they're essentially the same. In terms of the average projection, for New Brunswick following the RCP 8.5 is about 4-degree increase based on that RCM prediction. For the RCP 4.5, the projection is not as large. It's about 1.6 degrees. Now, what is an RCP? An RCP is a scenario that was decided by the people involved with the IPCC, the Intergovernmental Panel on Climate Change, on what type of scenarios people should be using so that we're talking the same language in terms of climate change. RCP 4.5, that 4.5 represents how much energy forcing or radiative forcing would result by assuming this particular scenario. That 4.5 is 4.5 watts per square meter. So it doesn't sound big, but once you integrate that number for the whole planet, it becomes a very huge number. The 8.5 is the same thing, is that there's an assumption that if we follow the RCP, which is representing concentration pathway of 8.5, there'll be a radiative forcing of 8.5 on top of what radiative forcing that actually currently exists. So this typically in terms of the emission scenario for RCP 4.5 is that the type of emissions that we're currently seeing by 2040 we'll have cleaned up our act to some extent, and we start using technology to try to offset the emissions being released. That's sort of the assumption under that particular RCP scenario. If that doesn't happen and we continue as business as usual, then we follow the potentially RCP 8.5, potentially even higher than that. So RCP 8.5 is what they classified as the higher level, but it's possible that we will actually exceed that particular scenario. Note that there's a lot of variation in both RCP's scenario over time, but again, the main point by 2100, there'll be an effective increase of 4 degrees for RCP 8.5 and 1.6 for RCP 4.5. So based on that information and based on the fact that this is the average, it's really difficult to show this information based on point by point opposed to an average, but I think you get the idea. But the idea is to put that information in terms of these maps. And these maps vary from 1950, this is where they begin the actual simulation, taking real data to actually calibrate the initial period such that when you go beyond 2020 or so, then you're dealing with what the future might hold. So these maps were based on satellite information. There's a lot of methods that can be used here. One method is simple interpolation. The unfortunate thing about interpolation is that it tends to mask effects like how lakes actually influence local climate and local forests. So we decided to use satellite information. These are compilations of about 400 MODIS images that put together gives you sort of an average trend in temperatures spatially. And then these spatial representations are modeled as a function of time. So the series of these images, this is for 1950, 1952, there's one for every year. So that amounts to quite a few images. So it really is trying to merge MODIS with the RCM data. So MODIS gives you what it is now, and the RCM data will give you what it will be in the future based on the RCP 4.5 or 8.5. Here's the growing degree day maps, same arrangement for different time slices from 2005 to 2090. And you get the series of snapshots if you want, and this string of maps relates to RCP 4.5. You see it's slowly warming, as you would expect, based on the RCM data. And this string of figures relates to RCP 8.5. And the warming gets much more intense, if you want, as we go into the future. So the colors, the redder the color, the higher the growing degree days. So if we go with current conditions, this would be what we have now. So this would be based on MODIS images, and then these ones are based on merging calculated regional climate model with the MODIS images. And so here we have indications where the heating is quite extensive. The differences you see in terms of the colors, the green here is in the highlands. So the highlands are cooler. They are cool even now, right? So that type of cooling in the higher elevation is something that's going to persist, right? But that gets eaten away slowly. So what warms up first is the low-lying elevations that will heat up the most, with the cooling areas or cooler areas becoming warmer as well, but not to the extent that we see in the lowlands. So in terms of precipitation, which is used to calculate soil water, we see that there's slightly more variation between the two scenarios, again, the blue being RCP 4.5 and the red being RCP 8.5. But you see a trend upward where by 2100, the expectation is that precipitation is going to increase by about 31% more than what it is currently. So it's quite an interesting feature. And in terms of RCP 4.5 is about 9 to 10%. Okay, so it's lower. So keeping things by trying to moderate these changes is a good thing to do, whichever way you need to approach it. And forestry is certainly something that people can look at from a mitigation point of view. The rationale of using RCM data is that there's a tendency for people to use, okay, it says that the temperature should be this much. And then over here it says something about precipitation. The problem is that those numbers are coupled. If they're not coupled, you can come up with any scenarios that you want. So technically, they have to be coupled, and only the RCM data can actually allow for that coupling. They're designed to deal with the dynamics of the climate system, which includes both temperature and precipitation. In terms of precipitation, similar maps are generated. We have variations that we see here because higher elevations, the wind speeds are higher, the precipitation is higher, mainly due to orographic processes. And so the RCM data are designed to capture these things. So statistical scaling, downscaling, can capture some of these things, but not to the degree that we have with these RCM models. Now, in terms of this, back to this model, now is to try to use the information and to look at things that relate to the water budget, and therefore a calculation of soil water. And here's a close-up of soil water. You note that soil water is not uniform. Soil water will vary according to the rolling of the topography. Water goes downhill and will tend to collect in the valleys. Now, in terms of this particular map, it's actually joining present technology that was developed at UMB, taking into account the wetted areas map. Probably a lot of you have come across that. This takes that into account in dealing with the water table. That's one element that this method doesn't address. It addresses how the water would evaporate, which is really not a water table issue. And so this actually couples the two together. Here we could do the same thing with LiDAR data. We get much more high precise information at a finer resolution. And you could apply many of the rules that I've discussed already based on using LiDAR data as your central piece of guiding the calculations. In terms of soil water, the expectation with soil water, these maps represent a percent change. They're not actual maps of soil water, but how soil water will change over time. It's not going to be uniform. We can see some areas here. For example, there's redding. The red colors indicate about a 24% increase from current soil water calculations. And you can see that in terms of RCP 8.5, there's actually greater increase in soil water content in the northwest of the province compared to what we see here. But in terms of the previous time slice, 30-year time slice, we see that, in fact, this area would tend to have a higher increase in soil water. Now, one argument lies that I've been advocating that the climate will tend to get wetter. In fact, current data indicates that. Okay, current data from 1950 to 2020, there's an indication, over the last 100 years, there's an indication that the climate will get wetter. These are maps produced by NRCan. And in fact, they're proposing similar pattern. The New Brunswick here, this is current. This is the reference period that they used, 1981 to 2010. And it's indicating that the blue colors indicate a wet climate. The tendency in terms of climate change is that in the Western world, the tendency will be that wherever it's wet, it's going to get wetter, okay? And in the same area, wherever it's dry, it's going to get drier. So if you look in terms of the prairies, the expectation is that it's going to get drier, suggesting something about the food element of Canadian society. NRCan data shows the same thing. The projections for 2071 to 2100 is that the New Brunswick will get wetter. Okay? But because it's getting wetter, it doesn't mean drought is impossible. In fact, drought can occur. It really depends on the precipitation that occur within any given year and the temperature for that year or that month. So it's possible to get drought, but the likelihood of drought is not that high. Okay? So we will have to be tending with more water than we really have an ability to deal with. And so that suggests certain things in terms of harvesting the soils and so on and so forth. Yes?
So with that as well, we're probably going to see more extremity in drought and water events as well, right?
One of the expectations is that the variability will increase. And so it's possible that you might get a very severe event, but the overall picture is that the trend is upward in terms of wetness. But it's possible because of the relationship between precipitation and water, right? So to just put numbers together and to suggest that there's a drought every year is wrong. You have to look at the connection between these two variables. And they have to come from a similar source. The RCM is the similar source. And that will tell you what is the balance between these two variables. Yep.
These are annual maps, right?
Yes.
So are you, maybe you couldn't hit it, are you going to look at seasonal? Like,
I
you
don't.
have an annual increase, but if it's all in winter, it's very different.
That's right. Those I don't have those, but you're right. It's not uniformly distributed in terms of season, and Bill is alluding to certain relationships in terms of water and temperature, and it might even, in fact, affect the winter period more than what we see now. And that might relate to thaw freeze and embolisms in trees, which is not a very good thing to have. No, unfortunately, I don't have that, but we could generate those for you if that's of interest. Now to modeling wind. We modeled wind not because of its intrinsic destruction. Of course, that's part of it, but also because it has an ecological function in trees. In areas where trees where the wind is high, the trees tend to be shorter because during events of high windiness and due to possible desiccation, the stomates close. And in closing, will have an impact on the tree growth over time. So if it's consistently windy, just think in terms of going to the coast versus inland, or high elevation versus low elevation. There's a consistent pattern that those trees are very different in terms of their growth, vertical growth, but also in terms of their diameter growth.
It's very interesting you mentioned desiccation. So are you referring to the fact that in the evapotranspiration process, water is being wicked away quicker so that atmospheric pressure of pulling up water is more difficult? Like trees are actually balancing.
That's right, there's a trade-off.
I can.
That's right, they need water. Right? But they also, if they keep on losing water, they have to close off their stomates to prevent excessive desiccation. In the process, they can't take up CO2. So the process is both ways, right? So there's a trade-off. Do they keep their stomates open while they're losing water? Most likely not, right? So based on RCM data, we can actually project maps very similar to the series of maps we talked about, temperature and precipitation, where typically the windier areas are in the high elevation areas. And going back to this, here what we've done is look at specific PSPs. Okay, this is done at the plot level. So each plot would have its own series of trend lines with respect to different, this is actually for 4 different PSPs, and you can see that the general tendency is the same, but they're displaced. This would be for growing degree days, this would be for relative soil water content, and this would be for wind speed. And those plots involved here relate to these points with an arrow indicated there. So here are some plots looking at real plots, real data, and calibrating each of the plots to generate these types of plots to see how well it represents the actual biomass and use that information to extend beyond into the future. The reason that you see these error bars is that the model, because of its stochasticity, has an element of randomness, especially in terms of regen and mortality. We run the model many times, and that middle line represents sort of the long-term average. That represents probably, it gives you a better sense of the, you know, the direction of the various values. The biomass is based on information. This is from a paper, Lambert's paper 2005, and using information from the tree, individual trees within a plot, we can come up with estimates. And it's based on the different parts of the tree. And then you simply total these values to get a total tree biomass. So in terms of plot level changes and species for RCP 4.5, from 1987 to 2100, northwest New Brunswick, this would be what you would get. And the initial conditions at this plot, for this particular plot, is based on what's actually there now. So we take that and extend the simulation further into time. And this plot is actually right here, so it's in almost within a valley itself. And because of its position, you might see differences that seem to be relevant to its position. Then we go to RCP 8.5. Now we see balsam fir dropping a bit more. And if we look at the changes with RCP 4.5 and RCP 8.5, we get a definite decrease in balsam fir biomass over the time period indicated for this particular plot. Now, my particular area of interest relates to looking at whole landscapes, because the landscape, the shape of the landscape will define where water is high, where water is low. And it's to put that information together and treat the calculation based on the individual cells that make up the plot. So individual cells will have their own, you know, moisture levels, temperature, and all of this put together will determine which species will tend to grow or not grow in an area. So this is the total biomass. Oops. This represents the total biomass, no matter what the species are, and these are broken down according to species, given a warming climate. This in particular is red oak. Red oak will tend to do better as you get into the future. Also, we do this type of work relating to species distribution model. This is for balsam fir. And using MODIS information, it allows us to look at detail that you would never get by interpolation. So MODIS data allows us to see what the climate conditions are next to lakes. And because lakes, especially deep ones, actually moderate the local climate. Okay, typically, from a scientist's point of view, that I find interesting. But maybe for everyday operations, you might not want that type of level of detail. But as a researcher, I thought that was important to do. So here are the red colors. It's the same scale. Go from 1, meaning that the possibility of balsam fir being present is high, with close to a value of 100%. In this case, we simply use the scale from 0 to 1. And as you get to the darker colors, the tendency of the occurrence, probability of occurrence decreases. And so this type of model can be used, again, as a tool to looking at, just for balsam fir, what is the potential with climate change. Here's an example of that. This is in northwest New Brunswick, where it tends to be cool already. So the response of that region will be different than, say, in the lowland areas because of their location within the larger landscape. And that's it. So I assume if there are any questions, I'll be happy to address. Any questions?
Under higher RCP, becoming less predominant?
That's right. Typically, when you look at balsam fir, especially in the north, a lot of it tends to be in sheltered areas and also in cooler areas, but not enough that it's affected. If it was higher elevation, it would be affected. So yes, what you saw there was that to some extent that area is protected for some region because overall it's higher elevation than what you would see in the south.
So if you consider balsam fir through its life cycle, from germination to growth as a small tree to mature to dying.
No, these maps refer more to the probability of that species being able to live in a certain area. So it doesn't deal with the sequence of growth from regen to full-grown trees.
So what factor causes the balsam fir to become less likely to survive?
Most likely the growing degree days or temperatures are becoming too high in some regions as being the predominant factor.
Is that more to do with water perhaps than actual temperature, water availability?
It has, but where they're located, the water availability is pretty high still. But it's, yeah, you're right. All of these things work together, and how to tease them apart sometimes can be difficult, but it's doable. And I suspect it's mostly driven by differences in temperature.
So that difference in temperature, is that because the higher temperature gives an advantage to the deciduous tree, for example, with a longer growing season?
Yeah, but we don't look at that. Yeah, that's a possibility, and the balsam fir could be at a disadvantage to the point that it doesn't become part of the landscape.
So as opposed to the balsam fir trees not being able to take advantage of that warmer climate, higher growing degree days, because they're being outcompeted by.
Yeah, it's too warm for them. If you look at their niche, it follows a sort of a unimodal function where it becomes bad when it's on the lower limb, as on the left-hand side limb, as well as becomes worse as you go on the right-hand side limb. So it's like a, in the middle is probably optimal conditions for them.
If you have a managed plot where the competing species are eliminated.
Okay, I'll leave that to my colleagues. They are addressing that type of question, probably more to the level that you want an answer for. So I'll leave that for them to answer. Okay?
I wasn't really going by the sea.
Oh, I wasn't concerned. So, but they will talk about at the stand level and all of these processes at work and how it relates to temperature and things like that. Is that correct, Gaeta?
Yeah.
So? So, yeah. Anyways, they'll give you a more wholesome picture of that, I think, than what I can deliver. Yeah.
Charles, do they take into account, your model predictions take into account any ability for the tree to adapt to changing climate over time?
No, it doesn't. Yeah. There's people looking at the plasticity of balsam fir, and but that's not an area I've touched at all. I'm aware of, but I haven't addressed that at all. So what the assumptions are is that what we're dealing with is based on what we know about the species now, opposed to what it might turn into. But the rate of changing genetically might be low, depending if it's being manipulated somewhat in the lab. I know some of that activity is happening. So that could be part of the picture as well. But in terms of this, no, I don't address those issues.
On a landscape level, that's a pretty important thing to touch on, is that the rate of change in climate.
It depends what you define as landscape. Yeah, if it's all of New Brunswick, I potentially agree with that. But if it's a smaller location, probably it's not. So it's an issue of scale, I think.
Sure, absolutely.
Yeah.
But you look at provincially, balsam fir is probably our second most predominant tree species in the province.
Yeah. Yeah. Still lots to be learned. Yeah. Anyways, I think, oh, yeah, you have a question?
Ralph, I just have a question on your maps and your data. Would that be something that would be available and like can it be posted to be used for doing a risk and vulnerability assessment for
Yeah. Yeah, it's available. I wrote, as part of the ETF funding, I wrote like several reports, which you have, but the data, if you want, it's available.
Is it posted right now in kind of a website
No.
that everybody can access it?
Anybody comes and see me, they can access it. It's just, it's not in a formal way. I'll leave that to the experts. I don't want to do that myself, but if somebody wants to do it and put it online, that's fair game. I'm okay with that.
I just had a question, second question on your wind projections. I didn't catch clearly, but is that something that is that we are going to see more powerful wind getting our species, or what's the what are the models telling about the wind?
I didn't get the question.
What's the
Maybe I should walk up.
with regards to your climate indicators that on wind, what is the scenario like for our province to see for RCP 4.5 and 4.5?
Between the two,
Yes.
I would suggest 8.5.
No, I mean like are we going to get more stronger winds or like?
No, winds, according to what I did, the winds are predominantly stronger. They'll become stronger along the coast where you have a biggest temperature gradient. The winds inland, even high elevations, do increase, but not to the extent they increase along the coast. But if you superimpose on top of that hurricanes, well, there's a lot of things about hurricanes, stalling mechanisms. You see some hurricanes in the south, they'll stay in a region for a longer time, and it's all related to these major questions about hurricanes, and it's possible that you might get a dump of rain that you've never seen before. So there can be impacts, but that's beyond my scope. But with the regional climate model, potentially we could start looking at those issues. Right now we haven't done that. The students just came to me last year, but we have plans for the near future.